Hey Chem Kids, Campbell here. In our second video on Chapter 16 Chemical Kinetics, we're going to talk about the factors that affect the rate of a reaction. Now, if you remember back to the first video, I talked about collision theory. And collision theory says that in order for a reaction to happen, the molecules have to collide. They have to collide in the right orientation and with enough energy. So in order to identify the factors that affect the rate of reaction, we're going to focus on those things. So in order to increase the rate of a reaction, we'll need to increase the number of collisions, right? The more they collide, right, the more chance they have of being in the right orientation with enough energy. The second thing we can do also is increase the amount of energy that they have, right? That will give them more activation energy when they come in and collide, and we'll also get more collisions. So we can increase the number of collisions or the energy of the collision. But how do we do that? Well, first we should look at the factors that affect reaction rates. So the conditions that affect reaction rates, one is the nature of the reactants. And in fact, that's kind of like when we talked about how much things dissolve, right? It was about the nature of the solute and the solvent. Well, for reaction rates, it's about how stable those bonds are. So the nature of the reactants that I combine. If the bonds are real stable, they're not going to react. But if they're unstable, oh yeah, we get a reaction. Other things that affect reaction rates are temperature, the concentration of the reactants, the particle size of the reactants, and the presence of a catalyst. So we're going to talk about the things that we can change, right? The nature of the reactants is what it is. That's just a function of the bonds, and I can't affect that. But I can affect temperature, concentration, particle size, and presence. So let's talk about those things. Now, think about temperature. If you remember back to our first unit from the semester, when we talked about kinetic molecular theory, we said that temperature is a measure of the kinetic energy of the molecules, which means that temperature is related to speed. More temperature, more speed. And so if we increase the temperature, we speed up the reaction because, one, we increase the number of collisions, right? They're moving around faster, so they're going to collide more often. But it also increases the energy of the collision, right? As opposed to if they're moving slow, right? Ooh. But if they move fast, boom! So increasing temperature does two things: more collisions and more power. Temperature's good. Concentration also has an effect. So think about it this way, from a collision standpoint with my little bubblegum machines. Here, I don't have a lot of reactants, so the concentration is low. But if I increase the concentration of the reaction, I'm going to get more collisions, right? Because they don't have far to go before they bump into something. So increasing the frequency of collisions happens when we increase the concentration. Particle size, just similar parallel to our chapter 14 molarity unit. If I can increase the surface area, so if I make them smaller, then there's more reactant exposed for collisions. I have a little picture here that kind of shows that. So if we have a solid here, and these red things are my other reactant, my two reactants, right, the red is, in order to get to the middle, right, we're going to have a lot of collisions because we got to get rid of these layers on the outside before we can get all of it to react. But say we don't have a solid, maybe we crush it up or we put it in a solution so it's dissolved. Now I have more particles exposed to the other reactant, and so my reactions can happen. So if I can decrease the particle size or increase the surface area, I have more reactant exposed and I can have more collisions. I also have a really great demonstration of that. So I'm going to show you a little video.
Now, watch this. Take your finger and then dip your finger down inside and watch what happens. Ready? So dip your finger down inside and pull it back out again. Perfectly dry.
Oh, for heaven's
Isn't that
sakes, no water,
amazing?
just like a podium, but
Yep.
no water.
You got it. So it's hydrophobic, meaning water-fearing. Dip it down again and take a look at it. So it used to be the coating on vitamins.
I can feel the temperature of the water,
Isn't that
but I
amazing?
can't feel the
Yeah.
water itself.
Special effects artists, honestly, the burning sensation will go away in weeks, so it'll be fine.
And
now,
the rash.
Yeah.
The
Now,
burning sensation and the rash.
put your glasses on. Put your glasses on. So now the other.
So
thing
that
is
wasn't
that
the cool
special
part.
effects artists,
This is the
and
particle
you
size
imagine
part.
on the Ellen Studio, the people that are around. By itself, watch this. If we put a little lycopodium here and we're going to light it on fire, absolutely nothing
This
happens
can't
at all.
be.
Look,
Oh.
see? Nothing happens.
It's
It's kind
inert.
of like lighting a campfire. You have to stack the logs up so that oxygen can get around it. If you were to take this, however, and disperse it in the air, then we've got oxygen around each little particle. So here, light this on fire. So go ahead and it's okay, just strike it. And push it forward. No, you have to stay.
Wait a minute.
No, push that. Yes, now.
He can't light a lighter.
All right, so you just stay and watch and enjoy. All right.
Okay.
So now just a little bit as it sits here.
Oh,
that's amazing. So this is what happens when you
That
have
was a
oxygen
coating
around.
for vitamins?
Well, but it's not used for this necessarily. I mean, there are many properties of something like that. So this is what we showed in the Ellen show. They wanted kind of a bigger fireball, and so here's what we have.
Bigger fire.
Yes. Don't do this at home. Right. It's lycopodium. Lycopodium is a spore. It's from a club moss. So here, watch this. So
A what?
A club moss.
Oh.
Yeah. So this kind of goes in here like this, and now here, watch.
Oh,
Ready?
here we go.
Oh, isn't that amazing? Wow. Is that fun?
Phenomenal.
So, but again, it's one of those things that they ask for out there because it just seems to be getting.
All right, so more particle size, right? When he blew the powder, more reaction. Totally cool. Now, another thing we can do is use a catalyst. And what a catalyst is something that we can put in the reaction that will increase the rate of the reaction without getting used up in the reaction. And so what happens with a catalyst is what a catalyst function is it lowers the activation energy. So this blue line here in this diagram is the normal reaction. There's my activation energy, there are my reactants and products. Hey, is that an exothermic or endothermic reaction? Exothermic? But what a catalyst does, this is the red line, it lowers that activation energy. So it facilitates the reaction. It's like a facilitator. And I have a little picture or a little demo here of that. And here is my catalyst. It's a platinum catalyst. And I have ethylene and hydrogen gas. And what happens is they bind to the catalyst, the platinum, and that facilitates this hydrogen from breaking apart and moving on to my ethylene. So there we go. So a catalyst, notice it didn't get used up, it's still the same as it was, but it's like a facilitator. It brings people together, I mean it brings molecules together. So that's what a catalyst does. It lowers reactant activation energy by bringing them together. It helps facilitate the breaking of bonds and the forming of new bonds. A good example of a biological catalyst is in your body, enzymes. So the enzymes in your digestive tract help break down protein molecules in a few hours. And it's a good thing you have them, because if you didn't, it would take years to break down those proteins. Ugh, I don't think you'd feel very good. All right, last thing I want to talk about are inhibitors. What an inhibitor is something that slows down or stops a reaction. Inhibit, inhibitor, stop. Inhibitors can work several different ways. One, they can raise activation energies, so they can raise that peak and make it harder for the reaction to happen. They could bind to an enzyme, so they could inactivate a catalyst like an enzyme, or they could destroy or damage it. So here is, for example, maybe this is my catalyst, and here are my reactants, and they come in and the catalyst facilitates them getting together. But what an inhibitor could do is it could bind to that catalyst and it would block it. And so now I can't get my reaction to happen with my catalyst. So inhibitors can do several different things, but they're not good for reaction rates. All right, that's all I got for you. Talk to you in class.